Okay, today we're going to look at an introduction to binomial distribution. And we start off with the question, what's the probability that if I roll 5 dice, that 3 out of those 5 would show the number 4? So we think about what are the possibilities of that? Well, first of all, we can arrange it. Well, what are the arrangements we could have? Well, we could have 3 lots of, the first 3 dice being a 4, and then the next 2 being not 4. Or we could have it like this. Or we could do it like this. Like that. Like that. We've got plenty of options. Like that one. And then perhaps we could go to something like this. That. Or that. Right, so we've got a few options, and in fact we can express the number of options by this. We use a combination. So we have 5, and out of that combination we want 3 lots of 4. Right? Now we're going to arrange this in an order that's going to just work for the situation. So we have our 4s, and then our non-4s. So what's the probability of, the next thing we ask is what's the probability of getting a 4? Well, we've got 1/6. And then how many 4s we've got? We've got 3 of them. 1, 2, 3. Then we have our non-4s, and we have 2 non-4s. So in each one of those there are 5 options. Because it wouldn't have mattered if that was a 3 or a 5 or a 2 or a 1, anything that's not a 4. So there's 5 options, and we want to have 2 of them. So we have, first of all, the total number of outcomes that we could have, then the probability of success to the power of how many successes there are, then the probability of a failure to the power of the number of failures that we had. Right, so in this case, 5C3, we can bang that in our calculator and find out the answer for that is 10, times 1/6 to the power of 3 is quite a small number, 0.0049, or 46, sorry. .463 times, and then 5/6 to the squared is 0.6944. Right, so if we multiply all of those together, we get 0.03215. Right, which is about what we'd expect. If we roll 5 dice, we don't expect to get 3 very often, 3 4s very often. And so here, 3%, that probably feels about right. We can then formalise that probability to be, if we were to then say, well, if we had n trials, and we wanted x results with a probability of p. Probability of 1 being p. Our formula comes out like this. The probability that a randomly selected one is equal to the one that we're after equals the combination between n and x, right? And then times the probability to the power of x, because we have x number of our outcomes, then times 1 minus p to the power of n minus x. Let's just zoom over here a little bit, I'll tidy that up. No, that's going to be as good as it gets. All right, so to look at that in a little bit more sensible, let's have a look at one problem, and I'll get you to do this. Okay, so I have 6 cats. Each one has a 1/4 probability of catching a mouse in any given week. Now, we're assuming here that those probabilities are independent, that if one of them catches it, that there's not less mice, and so the probability won't change. Okay, so I first of all write down what are my parameters. My n is equal to 6, because I've got 6 cats. My probability is equal to 1/4. And my x, what I'm looking for is I'm looking for if there's 2 of them. Okay, so then I write out my equation. Probability that x equals x is ncx p to the power of x, 1 minus p to the power of n minus x. Okay, so we then put that with the numbers. The probability that my randomly selected one happens to be 2 equals 6c2 times 1/4 squared times 3/4 to the power of 4. Okay, and that equals 15 times 1/16 times 81 over 256. That's going to be too nasty to write as a decimal, as a fraction. So instead what we're going to write is a decimal, 0.2966. So we'd expect that almost 30% of the time we would end up with exactly two of our cats catching a mouse. Here's one for you to have a try with.